In this video, we're going to look at Rolle's theorem and the mean value theorem, which are both important in talking about some applications of derivatives. Alright, here's Rolle's theorem. Let f be a function with the following properties. F is continuous on the closed interval from a to b, and it's differentiable on the open interval from a to b. So it doesn't have to be differentiable at the endpoints. And we impose the third condition that f of a equals f of b. Rolle's theorem says that if those conditions are met, then there is some number c on the interval from a to b, not including endpoints, where f prime of c equals 0. So here's a diagram. So first of all, we have that the function is continuous on the closed interval from a to b. It may not be differentiable at the endpoints, but we also have that f of a equals f of b, so these y-coordinates are the same. Well, if the graph went straight across, then there would be plenty of places where the derivative was 0. But what if the graph doesn't go straight across? Well, suppose it goes up. Well, if it goes up, it's going to have to come back down to make the y-coordinate at this end the same as the y-coordinate at that end. And it's not allowed to, the turning point is not allowed to be a cusp. It has to be a smooth transition from going up to coming down. And so where the transition occurs, the derivative is going to be 0. So can we give an example of a function that shows that if condition 1 is dropped, then the conclusion may not hold? In other words, there is not a place where the derivative equals 0. Well, what's continuous? Condition 1 is that f is continuous. Well, actually, if we drop, okay, let's see this. So I want the function the graph to pass through this point and that point, or to include these 2 points. But how about we do this? The function is differentiable on the open interval from a to b, and f of a equals f of b, but the function is not continuous on the closed interval, and there's no place where the derivative is 0. Well, there might be one here, but if I had drawn the line straight, if I had drawn this line segment straight, then there would not be one. Give an example of a function that shows that if condition 2 is dropped instead of condition 1, then the conclusion may not hold. And so that means we're going to add in the we're going to add back in the continuity condition, but take out the differentiability condition. Well, you could have something like this. Now the function's not differentiable on that interval, but it is continuous, and f of a equals f of b, but there's no place where the derivative is 0. Finally, is it possible to add back in conditions 1 and 2 and drop condition 3 and come up with a function where the derivative is never 0? Alright, so in this case, f of a doesn't have to be f of b. Oops. Well, let's make that f of b and ignore that part. So the function is continuous and differentiable, but f of a is not equal to f of b, so there's no place where the derivative is 0. So you have to have all 3 parts to guarantee that there is a place where the derivative is 0. Alright, let's take a look at this example. And it should not say mean value theorem, it should say Rolle's theorem. If the given function satisfies the condition of the mean value theorem, find the value of c guaranteed by the theorem. Otherwise, explain why the function fails to meet the given conditions. Alright, so what we need to do is check the three conditions. Is the function continuous on the closed interval from 0 to 2? Well, it's a polynomial, so it is continuous everywhere. Is it differentiable on the open interval? Well, the derivative is 3x squared. The derivative is 3x squared minus 4. And that's defined for all values of x. So it meets the differentiability condition. And finally, does f of a equal f of b? So does f of 0 equal f of 2? Well, f of 0 is 0, that's nice. And f of 2 is 2 cubed minus 4 times 2, which is 8 minus 8, which is 0. So all three conditions are met. That means, according to Rolle's theorem, there's a place on the open interval from 0 to 2 where the derivative is 0. Now, Rolle's theorem doesn't tell us how to find that value. We've got to figure that out on our own. But it's not too hard, because here's the derivative right here. And so we just set that equal to 0 and solve. Pull the 4 over, divide by 3. X is plus or minus 2 over the square root of 3. Now, the value of c, well, there may be more than one, but those values have to lie on the interval from 0 to 2. Well, the negative value in this case doesn't, so really what we want is that c equals 2 over the square root of 3. We want only the positive root.